let's look at a quick example of some of the ideas that we did during the last session. And I posed this as a problem, example problem, but it could easily well be a lecture. And so either one. Uh, but as a question, find the magnetic field at a point Z above the center of a circular ring of radius A and N turns, all carrying the current I. So um, what I have is a circular ring, which I put in the XY plane, and the Z-axis is above it at center, uh, perpendicular to the plane of the loop. And so I want the field up here at this point, a Z above the center. Uh, it really has N turns, but I'm only going to look at one turn, one wrap, so it's like if N were 1, and then I'll put the N back in at the beginning. You can do some simple geometry on it. Remember, we want to use the Biot-Savart law to compute the magnetic field up here. That's the only thing that we really have to compute the field produced by this current carrying loop. And so I consider a small piece of current, IDL vector, over here, and it's a distance A away because it's on this circle, and this height Z, and so this vector that points from the piece of current that's producing the field to the point where that infinitesimal piece of current has produced the field is this vector R vector, and its length is, well, this is just a right triangle, and so it's Z squared plus A squared using Pythagorean relation. And this problem actually works best if you use some symmetry arguments. And you'll notice that for every piece of current IDL over here, exactly 180 degrees away from it, there is an IDL, same same magnitude of the length, but going in the opposite direction. And if I look into into both of these, I get this side view picture. And here's our ring. On the left-hand side, that's looking over here at this one, my IDL is coming right out at me. And I look on this side, that's looking this direction. The IDL is going away from me. So there's our currents and the IDLs. Here's our height Z. Oh, let's see, I had some auxiliary variables here. I defined this variable alpha. Yeah. Here. But if you just consider the direction only for the magnetic field produced by this IDL up here at the point at the height Z. Well, I've got I going into the page and R vector going toward it, and so this current over here is producing a vector B, really dB, that's going in this direction. And likewise, the one 180 degrees from it, if you do the right-hand rule for it, I dl vector cross R. Remember, R vector goes from the current to the point in question, and the right-hand rule, if I is coming out, then the magnetic field produced by this piece of charge over here is going in this direction. And one can resolve those into pieces parallel. So I just resolve the Z components and the one parallel for these two segments here. And you'll see immediately they're the same distance away. They're the same current, the same length, and so the magnetic field portion is, the magnitudes are the same. And so these parallel components are equal and opposite, and they will cancel out, whereas the two Z components will add together. And if I define this angle here in this little right triangle to be alpha, then this is a right angle here, and so this angle is 90 minus alpha. This is a right angle, and so this angle is alpha. And so parallel component is going to be the magnitude of b times the sine of that angle alpha. Well, I'm only going to look at one component, and I'm just going to look at the one on the right now, but I'm only going to look at the z component of that. Right? And the z component is the magnitude of b, dB really in this case, because it's not all the magnetic field at this point. It's only just due to this little piece here. I realize that I don't have to worry about these parallel components because they're going to cancel out. And I'll just get this dB and then add them up as I go all the way around the ring later. So the magnitude of the z component up here, just due to this IDL, is the magnitude of dB times, well, the opposite sine of this angle alpha. And now then I use the Biot-Savart law. Biot-Savart law is just this, for this IDL that's on this side. One can take the magnitude of this cross product. That's there's some constants, but the magnitude of the first one is IDL. Magnitude of r hat is just 1, it's a unit vector, times the sine of the angle between dl vector and r hat. Let's take a look at that. Well, dl vector is going into the page over here. Okay? And r vector is this vector that is going here, and if you can take a look at it, they're at right angles. In this picture, it's if I'm viewing right flat on to this right triangle, then this is going into the page, and r vector pointing from the charge, from the current producing the field to this point where I want the field, is in the page, and so they're at 90 degrees, and so the angle between the two is 90 degrees, and so I get the mu naught 4 pi, I, the magnitude of dl, it's just dl, r squared, magnitude of r hat times the sine of 90 degrees, the angle between dl vector and r hat. And that just turns in, of course, to 1. And then finally I put in the fact that I know what this distance r is. It's the square root of z squared plus a squared. So I plug that in here for r squared. I just need to calculate the sine of alpha. And here is alpha, so the sine is the opposite over the hypotenuse. And this side is square root of z squared plus a squared. Maybe better over here. This is a right angle here, and this angle up here is alpha. And so the sine of alpha is a over square root of z squared plus a squared. So sine alpha, a over the square root of z squared alpha. Now that, as I predicated before, is simply for one term. And now if I have n terms, I just have to multiply this. Each one of them is going to give an identical expression up there. And so I just multiply that factor here by n. I cleaned it up a little bit. And then as usual, that's only a piece for n turns over in that one portion of the wire. Just the one portion right here. And so I need to add up all the IDLs all the way around the loop. And to do that, I've got the general expression here, so I need to add up all the z components all the way around the ring. And if you look at that, that's this integral over dl, but L to go all the way around, L goes all the way from 0 to 2 pi times A. It gives me the total length of the circumference of that circle of radius A. And so then I've added up all the lengths all the way around there. Now this works very nicely because I can pull out all of this stuff because I'm not changing as dl changes, dl vector changes. I'm not changing z, the radius doesn't change, i's not changing. All of these are constants, so I can pull them outside, and then it just is adding up all the dl's all the way around that ring, which is just the total length, which is just the circumference. And so circumference of a circle of radius A is 2 pi A. And we simply plug that in here. And I collect a few terms. I've got a 2 here, n, I, a pi I'll put here. A times A is A squared. We'll see why not to cancel some of these here in a second. And then, of course, the z plus A squared to the 3 halves. And now then, I just note that the total area enclosed by that loop is the area of a circle of radius A, which is pi A squared. So this pi A squared here, I'll write as that, write just simply as the area, so we can identify it here in a second. And the 2 will cancel one of these 2's. And so for BZ, the total Z component of the magnetic field, in fact, it's the only component there because the others in the integration, as I add them all up, they cancel each other. The horizontal components cancel out. I get mu naught over 2 pi r NIA over this factor to the 3 halves. It's all in the z direction, so if you like, and I'll do that here, I'll put in this in vector form, and since it's all in the z direction, I use k hat. And now then, I come back and remember some things from previous. A current loop has a magnetic dipole moment, and for a current loop that we have, it's the current times the area enclosed times the number of turns, and then the normal is in the direction of the k hat is in the k hat direction, and that's exactly what I've got up here. So one could write this in terms of the magnetic moment vector for this circular loop as mu naught over 2 pi, mu vector over z squared plus a squared. This is just a constant vector. And again, the analogy here is that this current loop actually produces a magnetic field now. It has a dipole moment, a magnetic dipole moment, and so it behaves like a little a bar magnet with a north and south, and the field lines are similar to a bar magnet. They're actually identical to it if I get very, very far away, or if I'm on the axis anyway, if I get very, very far away from the loop and I get this mu vector. And I'm thinking in terms of maybe this is an electron that's going around in the orbit of an atom, and so A might be half an angstrom or so very small atomic size, and this Z is a more normal distance, a few centimeters or something. So Z is much, much bigger than a half an angstrom in any event, and in that case, this term becomes negligible compared to the Z, and so you get this true magnetic field of a dipole, point dipole formula. So this is the one. We only did it along the axis, but one can do it in general and get a general expression, and you get this general sort of magnetic bar magnet type magnetic field about this current loop. Well, that's a fairly important example because as a result of this, it shows us how to make permanent magnets, naturally occurring, the ones that were first discovered. And again, we use this analogy. You think of electrons going around as circulating charge. It has a dipole moment, but from the previous results, that dipole moment also creates a magnetic field everywhere about it. So if I start off with, say, an unmagnetized piece of iron, I've got magnetic dipole moments in random orientation. And so their magnetic fields will tend to cancel each other out. I'll have as many going one direction as the other, and the magnetic fields associated with each one of these dipoles will on average, for absolutely totally randomized oriented atoms, will cancel out. But if I put them into a magnetic field, so now put them in an external magnetic field, B naught, what happens? Well, there's a torque on each one of these that causes them to align with the field lines at that point, magnetic field. And so if you wait some period of time, then you get an alignment like this. Now, if you turn the field off, well, the temperature, the atoms are actually jiggling around, and so they'll get knocked out of alignment pretty quickly in general. But we can see now how permanent magnets, these lodestones that were first started the subject of magnetism with permanent magnets, arise. You have some molten iron, maybe near a volcano, and this molten iron is actually in a magnetic field. So while it's hot and molten, it's very easy for these atoms to move around and orient themselves with the external magnetic field of the Earth. And then, if it cools very slowly in just the right way, then it binds these atomic atoms everywhere, so that they're locked into this orientation. And then, if you go and mine this and pull this out, you've got a chunk of rock here where all of these magnetic dipoles are going in exactly the same direction. Well, what does that do? Well, in general, in the interior, I'll have remember the arrow end is the north end, the other end is the south end. So I'll have a north pole and a south pole that tend to pretty much cancel each other out on these atomic scales all the way on the interior. So, but I'll have the two ends. I'll have a bunch of magnetic north poles of these all on this surface, and a bunch of magnetic south poles on this surface, and so you get the two poles of the magnet. And if things are right, it cools very slowly, then you rise with this permanent magnet. It also shows us how to destroy a magnet. One way, these are all aligned, is just to hit it a bunch of times with a hammer, a piece of iron with a hammer, and each time you hit it, it's going to knock a few more of these out of alignment, assuming that you've got a different orientation from the external field. Or another way to do it is to heat it up. So you raise these up to very high temperature. That frees up. You don't have to get all the way to the melting point, but just heat it up. And again, that will tend to send it back to randomizing and so the net field vanishes. So it's because of this collective orientation of atomic scale magnetic dipoles that all permanent magnets arise. Well, to our knowledge, the only way magnetic fields arise in nature, in terms of things that have at least been observed, is via currents. And they could be macroscopic currents that we produce, or microscopic atomic scale size currents that then produce the magnetic fields. So magnetic fields arise from currents.